Problem with summer, you don't know if it's really a cold or if it's
Pollen.
yeah, or so
I feel like you catch up like I did.
we don't have any labs. Oops, got it. Wait, let me pause my lecture.
You wanna,
Whichever one it was. Yeah.
Oh, do they work there? Is it
They both work.
Camtech or?
It's a GTDI. They do soldering.
Yeah.
They solder AT&T circuit boards.
Oh, really? And they
And I saw them, I don't know. They said both of them work there. One work on first shift, other one work third.
we're gonna look at flow. What is flow
the motion.
of a fluid? Of a fluid. It's the speed of flow of a fluid. So it could be a gas or it could be a liquid, right? And flow rates become very, very critical. In fact, they control it very precisely now in our automobiles. They've always controlled the flow. Even if you look at the older carburetors, they had a vane on it where they literally controlled the flow that was controlled by your gas pedal. Of course, now your gas pedal is basically just a sensor, right? You understand that?
Yeah, it's like a pop.
And then your engine control module is what's controlling your flow, and your airflow, and your gas flow, and all that stuff. Of course, we already know this. Then these are some of the sensors. We've already talked about speed, position, weight. We haven't talked about count, pressure. Flow is the one we're going to do now. Temperature, light. Haven't talked about thickness, time, gases. We talked about liquid level. Motion and position and all those are pretty much well in there together.
So the ones in red are primarily what's really over.
Right. Well, yes, if we have time, we're going to try to look at these.
Yeah.
So these are the ones that we've talked. The ones in red are the ones that we've discussed so far.
Green one's what we're discussing.
The green one is what we're discussing now. And of course, this is the list that we came up with. Most people come up with pretty close to the same list. I don't remember what actually we all came up in this class, but we do that. So we need to understand some units. So we got SI units. These are standard industry standard units. These are ISO or International Standard Organization. It's actually, we call it ISO. We arrange the words, but it's actually a French term. So standard units is liters per minute, standard liters per minute, cubic meters per second, are represented by E squared divided by second, and standard cubic centimeters per minute. Over here in the U.S., we use what? Liquids, we use the gallons per minute, and gases, we use the cubic feet per second. So these should be the ones we're really familiar with over here. But these other ones you need to also understand because, you know, we're getting a lot of international companies over even in our area now. And they're more inclined to use these guys. And of course, the companies that's been here for years are more inclined to use these. So basically, this is pretty much well a standard electronic or solid state sensor. We've got the sensing element itself. And then we got something, a transducer that basically takes the sensing element and converts it over to some type of electrical signal, right? And then this goes into the conditioning. So this is pretty much on all our sensors. So we've got an analog sensing unit element. Then we got something that's going to take that and convert it over to an analog signal. And then we're either going to leave it analog or we're going to convert it into a current if it's a 4 to 20 milliamp current with a sensor. Or if it's a digital sensor, then it's going to convert it from an analog value over to a one on or off, right? You understand that? So that's what the signal conditioning would be. If this guy gives us what we need, then we're okay. So if it's an analog sensor, a transducer, then odds are we would have that. But if it's an analog sensor, then we're going to convert it over to electrical. And then we might have to go to current loop, right? Understand that? Or we might have to go to this. Any questions on that? It looks like a pretty good test question. Of course, we have gauges. And of course, gauges can either be digital. They're more and more moving toward digital, but you'll still find a lot of analog. Well, they're not analog. They may not be analog, but they have dials. Right? Understand what I mean? In fact, these the airplanes that I worked on, they had still had a lot of dial indicators on them. And we literally would take those dial indicators and they had lines on them, we'd position them. So no matter, when everything was right, the dials would be straight up. So the flight engineer was the guy that sat in the center seat between the pilot and the co-pilot. That's basically what he did. He just monitored those gauges to see if anything was going on. And a lot of it, well, they're digital, but they have analog pointers on them. And what's nice about the analog pointers, it's just like on your car. You know, they tried to go to truly digital speedometers for a while, but they figured out these guys are actually causing accidents, kind of like cell phones and texting is now, because you literally have to look at it to see how fast you're going. You know, after you drive a car for a certain amount of time, you can pick up the speedometer out of your peripheral vision, and you basically know the units and you know the speed you're going without actually doing looking at it. So like I said, on the airplanes, all the fuel indicators, the inlet temperatures, they still use pointer dials on them, and they literally was arranged so when everything was okay, they did what? They pointed up. So instead of the flight engineer trying to look and see exactly what it was, if it wasn't straight up, they knew they had a problem or something was going on. So these are very, very popular. I mean, they might be literally digital in format. So even our meters, one of the higher quality meters has a digital scale on it, but then they have what they call a bar graph, which is basically a dial readout. And so, and we can see things that go on a lot easier. So if I'm looking at a digital readout and it's seeing something fluctuate, what the digits are what? They're just changing. The dial would be doing what? And we could actually see the minimum and maximum values and all that. So dial indicators are still very, very popular in because you can interpret them faster than you can a digital meter. The digital meters you have to literally look at, right? Understand that? Yeah, so we'd have to run it. You'd go in there and you'd look at like the fuel indicators and stuff, and they'd be tilted off to one side, and the turbulent inlet temperatures and the tack gauges and everything on the airplane. So flow, we've got different ways we can do this. We can do it with a differential pressure base. And those we have what they call an orifice plate, a Ventura, and a hedostatic, which is very, very popular still in airplanes. So the very last measure now of airspeed which would be flow rate, right? So an airplane measures its speed by flow. And one thing that it can do is it can measure its speed, and we'll look at that in a minute, by how much air is flowing over it. Of course, what happens is that air varies with the pressure developed by the air varies with altitude, right? So this is where the P-dot standard. A rotometer, a spring and tension turbine, paddle wheel vane, magnetic flow meters, and the ultrasonic. So these are the different types of flow meters, and there may be more, but these are just the ones that we talk about. So this is what we call a spring and piston. Can y'all see how that works? Yes or no? So how does it work?
The flow goes in, pushes against the spring.
It's a calibrated spring, so this is a real precise spring, right? So it's a calibrated spring. When it comes in, it literally pushes. How far it pushes that calibrated spring back is really a great indication of the flow. Now this has a dial on it. It's actually attached on to this guy right here. The shape of this column is pretty critical too, guys, on how it limits the flow left when you get past, right? This is a dial indicator. You can really see where the dial. I think on this one, the dial is actually magnetically connected to how it's running out. So this is a spring and piston. Pretty easy to understand how it works, right? Flow pushes against the piston and a calibrated spring. This is called an orifice plate. So literally, if you look into it, you see a outside tube, and then you will have kind of like a washer in it. Not like a washer, like a washing machine. And what this does is when it flows through, it creates a what? So it flows faster in here. The pressure is a little higher on this side before it hits the orifice plate. It's less on this side after it goes up. And the difference in pressure represents the what? The flow. Exactly right. These guys are pretty cheap, and this is actually one right here. I don't know if y'all can see it. I know this isn't showing up on the recorded video, but this is the orifice plate right here. And then it just flows in, hits the plate, flows out. Here's your two pressure sensors. No, I'm sorry. These are the two pressure, and then we would use pressure sensors, right? You understand that? To measure the difference in pressure, and then we just the indicator would just mathematically combine the two pressures, and then they use that to calculate the what, the flow. Are we okay? Ventura type. This works exactly on almost exactly the same principle, but on Ventura type. So Ventura means we just have a narrowing. And then it comes up and re-expands. So what happens, and this is the way our vacuum, this is exactly the way our vacuum generators over on the Amatro line and on the Festo line that creates the suction cup, this is the way they work. It uses a Ventura. So what happens, it's just like the way airplanes fly, is that when we come over here and move it through this smaller surface, it creates low pressure. So we have a higher pressure over here, a lower pressure over here, and what determines why does the plane have to get up to so many miles an hour before it can take off, and why does it have to run a certain speed? Because when it moves across the top of the wing, right, the bottom of the wing creates a high pressure. When it goes over the hump on the top of the wing, it creates a low pressure and literally creates lift. But you got to go fast enough so that it creates enough lift to cause the airplane to fly, and that's still amazing. So these planes, and they put 200 or 300 people on those things, and all that luggage and all that stuff, and you got them wings out there, and it can create enough pressure differential between the bottom and the top to lift that thing up. It's really, really amazing. So this is a very Ventura flow sensor, very, very popular, but it still works on the presence of differential flow. And the problem we have is that they actually keep the flow a little bit to create the difference on the pressure. So we get a pressure loss, a little bit of pressure loss between the left and the right, right? Yes. So this is very popular too. This is the PDOT static that we were talking about. So we always got to have a reference. So the PDOT is it's in line with the flow. The static is looking at basically the density of the material that's flowing. And this is what airplanes use. This is their last defense on calculating the airspeed. So if you ever looked at an airplane and went down the side, you'd see little holes on the side. That's the static. And then you'd see the PDOT tube sticking out the front. The PDOT tubes on the airplane had to be heated because you didn't want them to freeze up, and you had to cover them up every time the plane was out on the tarmac because dirt daubers like to build nests inside of it. So it had to keep the chaotic static fixed. And they would get real hot. And I'm not going to tell you that story. It's a good story, but I got a guy burned his hand real bad doing something he shouldn't have been doing. And that's what he told his wife. He burned it on the PDOT tube while he was checking it out. These are called rotometers. And you see what happens. It's just got a float. It's got a calibrated weight. And then the flow comes in from the bottom. A lot of fun with it. In fact, I got one using something similar to this. So the flow comes in the bottom. How much pressure depends on how flow rate depends on how far this goes up, right? And then we disconnect the valve or another type of thing. Based on gravity, height of the float indicates the what? Rate of flow. I think we got one of these. This is the only one that we got. Yeah.
You have keys together. The wire, road, this, go out, look like it. Right there,
This is the flow meter. This is the flow meter right here. This is actually the pressure. Now, what it uses, I don't know. It looks like it either uses the orifice plate or it uses the Ventura, which is the sensor right here. So this is the flow. This is the actual flow meter. And, this is the flow meter right here, and this is the pressure. So if you ever worked on a sure enough swimming pool, not one of these things you set up in the backyard, most of the time they have pressure and flow on the stone. This guy is also pretty neat. It's called the vein type flow meter. Can you see how this works? Yes or no?
Pressure on the lead.
Yeah, push it on the vein. Has some type of damper on it. So when the damper moves, it acts like shock absorber. That's exactly what it does. And then we come in and we push against the vein. It'll be pushed back by the amount of water flow. And then we measure that. So this is pretty popular, vein type flow meter. Are we okay?
Yes, sir.
This is pretty neat. This is called paddle wheel flow meter. I've seen these before. Can you see how this works? Yeah, normally we'll have magnets out here on the tip, small magnets, and then there's a Hall effect. These are Hall effect, probably not a reed switch. A Hall effect can trigger on a very small magnetic field. So it probably has a Hall effect sensor up there, and when these magnets go flying by, what you do, the Hall effect sensor picks up the pulses, and then it translates that. The speed of the wheel would be the speed of the flow. Paddle wheel meter. We okay there?
Yep.
This is a turbine type, which basically works on the same type principle. This is a really good indication. So here's the turbine. So when the flow comes across, it turns the turbine. The turbine has some type of sensor on here. This basically works the same thing as the paddle wheel. So it comes over here. Picks up the paddle wheel sensor, how fast the turbine turns, would you see how fast the rate of flow.
Yeah, that one's air only, isn't it?
No, this is really good.
Oh, really?
Yeah, it's just paddle wheel. So anything that's in motion, would cause this to turn, right? You understand that? So this would be like, you know, you're taking the blade of the fan, you could blow air across it, and even though power's on there, the thing will start spinning. Well, you could just as well do that with a fluid, right? There. So this works, these will work with either fluid or any fluid. And that's what a flow rate does. It senses the rate of fluid. And of course, a fluid is either a gas or a liquid. This would have to take some type of liquids or some type of thing that had the ability to accept the charge. So what we do, of course, is we generate a magnetic field, and then the rate of flow in the particle. What determines how much, when we're using magnetics to reduce the voltages or something, what determines the amount that we use? So the fluid must be conductive or non-distilled water based.
What is non-distilled?
I mean, this distilled water is water that's all where the impurities have been moved out of it. So if I've got impurities in there, they're going to be magnetic in principle, right? You understand? They're going to be able to carry some type of charge. Understand? So distilled water, you know, you can stand in distilled water and it's non-conductive. Distilled water is non-conductive. And that's why you should put distilled water in your battery instead of putting regular water. Because what you want to do in your battery, the conduction, you want it to be controlled by the acid, right? Not by the water. And then plus, during this process, a lot of these impurities would be released and they would settle down at the bottom of your tank and they would eventually short your cell out. So a lot of people don't understand that and their battery. And that's why a lot of batteries are getting away from letting people even open them up anymore. Have y'all noticed that? And
It seems like they're coming back though.
But they're still very popular in lawnmowers. Some of your motorcycles are moving to what they call gel cells.
Yeah, I bought a gel cell for mine before I sold it.
And one advantage of that is you don't have to worry about tilt or anything like that. So a regular motorcycle, you got a drain on it. So when you tilt your battery over too far, you spill out the drain.
No, that never happened.
Yeah. So you check your. So when this thing moves, the speed of the rate of, so how much voltage we induce into something depends on several things. It depends on what type of material we're using, right? It depends on the number of loops or how much stuff we got to absorb the energy. And then, of course, one of the main things is how fast it's moving. So, example we would use would be probably this thing over here. So this galvanometer on it. We're going to add some resistance to the flow. And if you add resistance to the flow, then you're going to get a pressure. Now your sensor's creating a pressure difference, right? Y'all understand that? This guy right here doesn't do that. Picks up the flow rate using the induction principle of being induced by the rate that we move past. So this is pretty neat. This is called a magnetic flow sensor. Flow, but the only disadvantage is this sentence right there. Fluids must be what? Conductive. This is a really, really popular one that we call what? These are ultrasonic. These other ones are really, really neat in that they don't impede the flow of the fluid. No, they just pick it up. Got So Doppler effect depends on a depends on a sonic conductive particle density flow profile. Of course, the biggest problem we have is affected by what?
So, velocity,
Density. And viscosity.
thickness.
Density would probably be more a gas, right? And viscosity is the thickness of a liquid.
That fancy word.
Yeah, so if you're dealing with anybody into oils,
Yeah, it's like a viscosity.
yeah, used to when I was young, we used oils, and it was a single weighted oil. And people would get up in the wintertime and they'd go out there, and sometimes their starter didn't have enough punch to start the car. So what we have now is we have oils that are mixed, right? You understand? We have dual viscosity oils. We have one that's a real low viscosity and one's a real high viscosity. So one of them protects us it allows us to start it in the summer, and then in the winter, then the low viscosity kicks in, right? Okay.
That's why you have a 5W30.
5W30, yeah. So, which is really, really neat the way they work. Yeah, diesels were so hard to start. Diesel engines were so hard to start that if you lived up north, they had heaters you put inside the oil tank to keep the oil from getting real thick like that. We went up to Joplin, Missouri in the wintertime to the school fair. And we ran an extension cord. We drove the diesel car up there. We ran an extension cord out of the hotel out our door and plugged our car into it. And we got up the next morning and it wouldn't crank, it wouldn't turn out. And it had 2 batteries on it too. And guess what we didn't realize?
Power.
The light switch, the plug was on the light switch circuit. So when we turned the lights off at night, we didn't heat our thing up. Doppler effect, time flight. So measures time, bidirectional flow, unaffected by temperature, density, and velocity, accuracy of 1% flow. So this right here is probably the most accurate. So Doppler effect, since it's a shift in something, right? Because of speed, you should be familiar with this because the big thing when tornadoes are coming in is the Doppler radar. And what they do is they're sensing the direction and also the speed of the air. And so when you get something moving one way real fast and the other moving the other way real fast, what's the 2 colors they use on Doppler? Green and red. So that's what they look for. They look for a green coupled with a red. What does that mean? You got one the air is moving away from the Doppler, the other one the air is moving toward the Doppler. And so what does that mean? It means you got rotation, right? So they can really, really tell now. So it's not affected by density, it's not affected by viscosity. It's got a 1% accurate. So this guy right here would be on top. And it gives you an electronic signal right off. If you're running the same viscosity all the same with the same density, this guy right here, the Doppler, would be cheaper. Time of flight. Plug out. Are we okay? Questions? Questions? So y'all sure are quiet. So these are Doppler effect and time of flight. So you can see they literally do what? They don't, what's nice about them is they don't have to protrude into that. And some of it, of course, the spacing between the Doppler is very, very critical. Because you shoot the beam out and then doing what? Yeah, measuring how much it shifted. Time of flight. I've actually seen these things where they just clamp them on and basically they look like, I know what I'm talking about. Clamps, just hose. So they can be temporary, they can be permanent, which is pretty. Everybody okay? Yes or no? And that's our flow meter. So which one did we look at? Back to the start. So we looked at differential pressure. These are probably the cheapest. These have been around for years. We looked at the rotor meter. Okay, in fact, I should rearrange this. So this guy right here was actually first, right? Spring and piston, turbine, paddle wheel vane, and then our two electronic ones. No, that's ultrasonic. I guess ultrasonic meters would be the time of flight and the Doppler. And the magnetic was the one. What's the advantage of these two? So what's the advantage of the magnetic flow meters and the ultrasonic flow meters? Yeah, they don't impede the flow of the fluid, right? I understand that. Of course, the advantage of these, of course, is the price. They've been around for a long time. These are proven. Everybody okay? Yes, no? Yes. So everybody okay on Orbis plate, Ventura, Geostat, TDOT, I'm sorry, TDOT status? Yes or no? Okay. We're gonna go to the lab. I brought some ice in. Somebody said they was gonna bring in a heater. Somebody else said they was gonna bring in theirs too.
Huh?
Didn't you say that last night?
I thought I could find one, but I think